Welcome to the lesson on computing partial derivatives. In this lecture, we're going to learn how to compute first and second order partial derivatives algebraically. Partial derivatives, second order partials, and mixed partials will be the main topics. So we've already looked at partial derivatives in a previous unit, and you've learned to understand the notation a little bit and how to estimate them from data and from graphs. And we're just going to give you some shortcuts for how to compute them if you have a simple function. So to compute the derivative of a function f of xy with respect to the variable x, in other words, find fx or df dx, we simply use the normal derivative rules, treating x like the variable, and we treat y like a constant. So let's look at some examples. If f of x equals x cubed minus 5y squared, then the partial with respect to x, we treat x like a variable, so the derivative of x cubed is 3x squared, and the derivative of 5y squared, since y is behaving like a constant, we just say that's one big constant and the derivative is 0. So we get a partial with respect to x of 3x squared. Similarly, if we want to compute the partial derivative of f with respect to y, the derivative of x cubed now is 0 because that's a constant, and the derivative of 5y squared is 10y, and we subtract, so we get negative 10y. If you look at another example, g of xy equals xy squared, the derivative with respect to x is going to be y squared because that's just the constant in some sense in front of the x. And the derivative with respect to y, again, x is now treated like a constant, and you just take a normal derivative with respect to y and get 2y. So the result is 2xy. So let's look at a example that we've looked at before, a wind chill sensitivity analysis, looking at a function that tells us what the wind chill is depending on the temperature, which is the variable t, and the speed of the wind, or velocity of wind, which is the variable v. So if we've got the wind chill function right here, and I want to know what the sensitivity of wind chill is to wind speed when temperature is held constant, and wind speed is 25 miles an hour, what I'm really looking for is the derivative of wind chill with respect to velocity. So when the wind speed changes, how does that change the wind chill? So I'm looking for the partial of w with respect to v, and I'm going to want to plug in these values I indicated, temperature of 5 degrees and a wind speed of 25. So let's compute that. Let's look at the function. This first part, if I wanted to compute the derivative with respect to v, that's simply a constant. Its derivative is 0. This second part, again, I'm computing the derivative with respect to v. So 0.6214t is also a constant because we're treating t like a constant. And so that derivative is 0. So now we actually get into something where we have to do something. This part, 35.75 v to the 0.16. With respect to v, that derivative requires we do a power rule, and we just bring down the power 0.16 and subtract 1. And so we get this part right here. And similarly for this last bit of the function, again, the 0.4275 is a constant, and t we treat as a constant also, so we just use a power rule on v, and we get this piece. So if I'm looking for the sensitivity of wind chill with respect to velocity of wind at temperature of 5 degrees and wind speed of 25 miles an hour, I can just simplify all those computations, all these calculations here, plug in t equals 5 and v equals 25, and I'm going to get this number right here. And the units of that should be degrees of wind chill per mile per hour of wind speed. So that means if my wind speed goes up 1 mile per hour, I expect about a change of a negative 1/3 degree of wind chill when the temperature is 5 and the wind speed is 25. Okay, so let's look at this now instead of with respect to wind speed, with respect to temperature. If I ask what the sensitivity of wind chill is to temperature, when temperature is 5 degrees, and wind speed is now held constant, that's simply asking for the partial with respect to t. And that's pretty easy to compute, and I'll let you try that on your own, but the answer you should get is right down here. And if you plug in t equals 5 and v equals 25, you get 1.33689. So what does that mean? That means If the temperature goes up a degree, I expect the wind chill to go up actually a little more than a degree, 1.33 degrees, when the temperature is 5 and the wind speed is 25. Okay, so let's look at some second-order partial derivatives. Finding second-order partial derivatives is just a simple matter of computing a partial derivative a second time. And the notation that we use is typically something like fxx if we're interested in computing a partial derivative with respect to x twice, or sometimes you'll see the partial symbol at d2f, and that just means two derivatives of f, and the bottom tells you you're doing the partial derivative with respect to x twice. So let's look at some of the partials. If f of xy equals x cubed minus 5y, we already know how to compute the first order partials, the partial with respect to x and the partial with respect to y. But now I want to look at this right here. That fx means I've already computed a partial derivative with respect to x, and now I want to do it again. So if I take the partial derivative with respect to x, which is 3x squared, and compute a derivative of that, treating x like the variable, I'll get 6x. So that's what that second order partial means. If instead I take the partial derivative with respect to x, so that inside variable is what we're taking a derivative of first, and then take a derivative with respect to y, if I go back and look, derivative with respect to y, that 3x squared is treated like a constant. There are no y's there. So I just get 0 for a second order partial fxy. Similarly, if I want to compute fyy, I look at the partial derivative with respect to y. That's negative 10y. And I take another derivative with respect to y, and I get negative 10. And I will let you just verify that fyx, which means take a partial with respect to y first, and then a derivative with respect to x, is just 0. If we look at another example, g of xy equals xy squared, then the derivative with respect to x is just y squared, and the derivative with respect to y is 2xy. If we wanted the partial gxx, that means take a derivative with respect to x, and then do that again. So if I take a derivative of gx with respect to x, I'm going to get 0 because there are no x's there. Similarly, gxy, if I took a derivative with respect to x, and I got y squared, take another derivative with respect to y, and I get 2y in this case. So second order partial derivatives are really easy to compute. There's really not a lot new. You just have to keep track of the variables. But let's think a little bit about what they mean. We're not going to go into too much detail here, but I'll give you some sense of what the second order partial might tell you. So if we look back to our wind chill example, we can compute a second order partial. So the first order derivative, the derivative of w with respect to v, or velocity, is given by that function. And the way we interpret that is the sensitivity of wind chill to velocity. What do small changes in velocity do to wind chill? The second order partial, if we take another derivative, we're now saying that's the sensitivity of the first partial with respect to velocity. So if velocity changes a little bit, how would that change that first partial derivative? In another sense, you can think back to single variable calculus, and this could tell you a little bit about concavity. So for example, if you know that the second order partial d squared w dv squared, if you knew that was positive, then you would know that the function w is concave up with respect to v. So if you held temperature constant and just looked at the cross-section of the function with respect to v, that part of the function should be concave up. Similarly, if that second partial were negative, then the function w, if t were held constant and you were just looking at a cross-section, would be concave down. Okay, so what you might have noticed as we were computing some of the mixed partials, so taking a derivative of f with respect to x and then y, we could do that in two different ways. We could take a derivative with respect to y and then x, and the question is, how do these things relate? And it turns out that the theorem for most of the functions we're going to encounter that have nice continuous second order partials, those second order mixed partials are equal. So let's just look at an example to convince ourselves. If we look at the function f of xy equals xy squared and compute the second order partials, and I'll let you do that, it turns out that those are equal, and that's going to happen in all the cases. That's a useful thing to know sometimes if you're just trying to check if you've done your work right. If you compute the second order partials and you get different answers, you might have made a mistake. So what I expect you to be able to do now is to recognize when you need to compute a partial derivative, to be able to compute those using the rules from previous lecture modules, and then interpret the meaning of second order partial derivatives. So thanks for listening.